In this video, I'd like to share some ideas for coordinating the frequencies and channels being used on your amateur radio emergency data network. This topic may appeal more to experienced AREDN folks, but it's always good to understand how these radios work as they communicate with each other. It might be especially helpful to understand why your radio's performance could decrease whenever you have two or more devices that share the same channel and you deploy them close together or on the same tower or rooftop. At a basic level, devices on each side of a radio link need to use the same frequency band and channel, the same channel width, and the same SSID. Beyond that, you have a lot of flexibility to select the radio channels that give you the largest signal margin and the highest data throughput on your radio link. If you have individual radios at different locations across an area, then all of those radios could use the same band, channel, and channel width. That way, they can establish a mesh network and route data to each other as needed. But as more nodes join the network, or when several nodes are co-located and share the same channel, it's possible for overall network performance to decrease. We'll talk more about the reason for this in a moment. Frequency coordination and channel planning become more important as a wireless network grows. To plan for future growth, local mesh groups may need to designate certain channels to be used in specific regions so that the network will perform well. The frequency bands used by AREDN radios are divided into channels, each of which consists of a 5 MHz frequency range identified by the center frequency of the channel and assigned a channel number. AREDN devices have the option of using either 5 MHz, 10 MHz, or 20 MHz channel widths. Different channel widths may yield better throughput than others. For example, long-distance links tend to have better performance using 10 MHz rather than 20 MHz or 5 MHz channel widths. Test the performance of your links using various channel widths. In this example, you can see that a selected channel may use more or less of the frequency range based on the channel width that's allocated. The wider the channel, the more overlap there's going to be with adjacent channels. Wide channels have the effect of decreasing the number of non-overlapping or non-interfering channels that'll be available for us to use. When selecting channels and widths, be sure to use non-overlapping channels. Devices using channels or channel widths that overlap will interfere with one another, and they can't communicate to coordinate the sharing of bandwidth. We'll talk more about this topic in a moment. You may need to use 10 MHz rather than 20 MHz channels in order to ensure that you have enough available channels for the links that you plan to implement. A moment ago, we mentioned the importance of using non-overlapping channels, and the concept of overlapping channel interference is illustrated on the left side of this channel scan diagram. Overlapping channel interference is very serious and should be avoided at all costs, but it can be easily eliminated simply by selecting non-overlapping channels for all the devices that are accessing your network. A second issue related to how wireless networks operate is illustrated on the right side of the diagram. It's commonly called co-channel interference, but it might be more accurately described as co-channel contention or even co-channel cooperation, since this negotiation process is by design. So on the right side of the diagram, we see several nodes that are sharing a single channel. They all negotiate for the opportunity to transmit. Any node that needs to transmit will use 802.11 listen before talk technology to determine whether the channel is clear. If the channel seems clear, the node will attempt to transmit data. If the channel is busy, the node will wait until the channel seems clear. In a very dense network where a large number of nodes share a single channel, this normal negotiation process could result in a performance degradation. From an end user perspective, an overloaded channel might make the network seem sluggish or unresponsive or even unusable. This example is not meant to say that having only 7 nodes will overload a channel. There really is no established rule of thumb for channel sharing that says how many nodes are too many. The answer depends on several factors, many of which are going to be discussed shortly. A wireless network is what's referred to as a shared half-duplex medium, so only one station should transmit at any given time. In that sense, wireless operations are similar to other types of amateur radio transmissions. If 2 stations key up their transmitters at the same time, they'll interfere with each other to the extent that neither of them is going to receive the other's message. That's why there are net control procedures to ensure that emergency communication is passed reliably during an incident. And so a similar concept applies to AREDN radios. You can think of the AREDN firmware as having sophisticated built-in net control capabilities. Radios access the channel by implementing several important wireless standards, including IEEE 802.11n and carrier sense multiple access collision avoidance, sometimes seen abbreviated as CSMA/CA. In simple terms, this listen before talk technology is what helps nodes determine whether a channel is clear before they transmit. With a single channel wireless network, any node that wants to transmit will automatically coordinate with the other nodes for a clear channel. It performs what's called a clear channel assessment to negotiate access to the channel. As you can imagine, when a large number of devices try to access a single shared channel, each node may have to wait longer for its opportunity to transmit. You can find additional information about these standards at the URLs that are shown here. In every wireless network, there will be nodes that are not within radio range of each other, but which are members of the same mesh network and share the same channel. In this diagram, node A can hear node B, but cannot hear node C. Since A and C are hidden from each other, they may try to transmit on the shared channel at the same time without being aware of a possible conflict. Because of their locations and typical network delays, each node may think it has a clear channel for transmission. To eliminate this problem, AREDN nodes can use request to send and clear to send messages, often abbreviated RTS and CTS. For example, when node A wants to transmit, it can broadcast a short request to send message with a proposed time slot and a duration for sending its complete data stream. Node B will receive that request and then it broadcasts a clear to send message for that time slot. Node C couldn't hear the original request to send, but it can hear the clear to send message. So it will wait during that time slot before attempting to transmit its own data. You can find additional information about this mechanism at the URL shown here. If there are too many nodes using the same band and channel, network users may experience poor performance. Here's a simple example to illustrate the issue. It's a 3-link path from node A to tower B to tower C to node D. If all of the links are using the same channel, then only one node at a time can send data. Well, this instantly cuts the throughput by half or more, and it increases latency with protocol overhead. To improve performance, you could configure each link to use a different band or channel. This allows the nodes to transmit simultaneously. For example, the link between node A and tower B could use 5 GHz channel 172. The link between the tower nodes could use 5 GHz channel 176. And the link between tower C and node D could potentially use 2.4 GHz channel -2. Before this kind of channel plan is implemented, it might be possible to have maybe one HD video stream and one VoIP call, both of which would have frequent dropouts. After a channel plan like this is implemented, it should be possible to have 3 HD video streams and several VoIP calls simultaneously with few dropouts. At some sites, there may be several devices mounted on the same building or structure. This photo shows several AREDN nodes installed on a mountaintop, for example. If co-located nodes share an RF band and channel, it can result in poor network performance. As we saw a moment ago, the network throughput for the site could be reduced by half or more. If you have 2 or more co-located nodes, then it makes sense to allow those devices to pass traffic over their Ethernet interface rather than forcing them to use their radio. This is called device-to-device or DTD linking. In its most basic configuration, an Ethernet cable is connected between the LAN ports of each device. The AREDN routing protocol will automatically assign a very low link cost to that Ethernet path, and it will then route traffic between the nodes over Ethernet rather than using the RF channel. One added benefit of DTD linking is that you can link nodes which are operating on different bands and channels. This bridges all of their traffic while avoiding the issues involved with wireless RF channel contention. Nodes that are using different bands or channels can still pass data at high speeds through their DTD links. At a mountaintop site like the one shown here, it's best practice to DTD link all of the nodes because otherwise RF channel contention could make the network unusable. It might help to look at a specific example of good channel planning at a real site that has co-located nodes. There are many excellent examples to choose from, and the one shown here has 8 co-located AREDN nodes. Let's focus on the 4 nodes that are using the 5.8 GHz band. If we use a 10 MHz channel width, which seems to have the best overall performance characteristics, then we could use every other channel and still have adequate separation between the adjacent channels. A good rule of thumb in the 5 cm band is to use only the even-numbered channels, each having a 10 MHz channel width. This gives you 27 non-overlapping channels that can be assigned as needed. At this particular site, the coordinators have selected channels 170, 172, 174, and 176. Your selection of channel numbers may depend on what else is already happening at your site. For example, you may find that using a lower or higher frequency range yields better performance based on the existing RF signals that other equipment at your site might already be generating. A spectrum analyzer could help you during your site survey since it can identify frequency ranges which are less utilized, and then you can assign channels within that space to your AREDN nodes. Even though it's not shown on this diagram, it's important to note that every single co-located node here is using a different channel from its neighbors, and this simple design decision has proven to give excellent network performance at this site. Depending on the frequency band you're using, there are various options for assigning non-overlapping channels to your mesh devices. As we saw before, in the 5.8 GHz band, using even-numbered 10 10 MHz channels, there are 27 non-overlapping channels for use. Each adjacent RF coverage zone should use a different channel, and they can be overlapped slightly to provide broader connectivity, but adjacent coverage zones should not use the same RF channel. This example coverage map shows that 4 different channels have been reused in the area to achieve broad coverage by segmenting specific areas into zones to reduce co-channel contention. Try to ensure that there is adequate RF separation between the zones that are reusing a particular channel. One thing to be aware of is that even a channel reuse plan like this may not eliminate all instances of contention. For example, if a node is at the outer edges of a coverage zone or is elevated well above ground level, its transmissions might propagate into a distant zone using the same channel. The radios in the other zone will wait if they hear that distant node's transmissions, even though they're coming from a completely different zone. Some degree of experimentation is probably going to be required in order to minimize contention and maximize your network throughput. Here's a summary of some of the things we've covered so far. Configure your co-located nodes to use different bands and channels, and then set up DTD links between the nodes to ensure that the traffic is routed efficiently without generating RF contention or delays. The OLSR routing protocol will give the DTD path priority when passing traffic between the co-located nodes. Consider putting each local coverage area on its own channel to minimize the interaction between zones. Be sure you have adequate RF separation between any of the reused channels across an area. If you need broad local coverage for a high-profile area, you could install sector antennas on a tower site. For example, 3 panels with 120-degree beam width each. DTD link the sectors at the tower site and use different channels for each sector to avoid channel contention at the tower. If you're installing long-distance point-to-point links to connect backbone sites or mesh islands, be sure to use a separate band or channel for each backbone link. This type of link has a single purpose: to carry as much data as possible, as quickly as possible from one end to the other. So eliminate any type of channel contention so that these links can achieve very high throughput. By way of disclaimer, I'm not an RF or network engineer, and this video isn't targeted to folks with that kind of background. The intended audience here is really amateur radio operators like me who want to design or deploy an amateur radio emergency data network. I've probably oversimplified many of the technical concepts that I've shared, but hopefully this can be a starting point for gaining more in-depth knowledge and skills with AREDN. Thanks very much for watching. I hope some of this information is helpful as you design and build your AREDN network.